All right, guys, so in the last section, we started introducing complex numbers. And in particular, one of the things that we saw was that for any given complex number on the complex plane, there are two equivalent representations or forms of the complex number that can be given. You can either write it in Cartesian form, or you can actually write it in polar form. Now, there's one last major simplification that can actually be made for complex numbers, but one incredibly useful and ubiquitous identity needs to be introduced before we can actually get to that form, and it's that of Euler's identity. So this is complex numbers. Still an overview, but I want to talk about Euler's identity. Now, what Euler's identity states let me write identity correctly. Strike three. Okay, fine. What it says is that if you actually have the cosine of an angle plus j times the sine of the same angle, right, then this is the same as e to the j of that angle, right? I'm going to state this without proof, but this can actually be proven using Taylor series or Maclaurin series for cosine theta, sine theta, and e to the I theta. If you actually go through the Taylor series of each one of those three, one of the things that you can prove quite easily is that the right-hand side is equal to the left-hand side. Now, this identity, essentially what it allows us to do is it allows us to turn trigonometric functions, which are in general difficult to deal with, into these exponential functions that have very, very, very useful and nice properties, right? This also means if we go back to the polar form of a complex number, remember, if we had a complex number in Cartesian form, which was of the form x plus jz, or jy, in polar form, this was r cosine of theta plus jr sine of theta. Notice that both of these terms contain an r in common. So one of the things that we can do immediately is factor that out. And inside of the parentheses, once we have factored out r, notice that what we have here is exactly what we have there in Euler's identity. This means that I can actually make the replacement with cosine theta plus j sine theta and rewrite it as re to the j theta like this, right? This is the improved polar form of the complex number. And you'll see that as we start going through defining how to do multiplication and division of complex numbers, this polar form is going to be much, much, much more useful to us than the Cartesian form, right? Another thing worth noting is something where on notation. We don't want to carry around absolutely everywhere this e to the j, right? The only really important parameters that will change as you move from one complex number to the other is the value of r might change and the value of theta might change. So another equivalent way of writing this complex number, and again this is notation, is that this is r with an angle theta like this. However, be very wary that anytime you see this particular form, before you can actually do an actual calculation, you must turn it back either into this form or into this form, right? But the notation that we actually have here, right, is going to be extremely useful as we develop, again, things like phasors.